I gave this problem on my mechanics final. It's pretty popular. It's a pretty common problem to solve, use for a Lagrangian example. So I made a little model of it, right, like this. See, you see that? So the idea is I have a loop, a ring, and there's a bead that can slide. And see, it's actually a piece of Lego. Actually slide that, and then this will turn at some constant angular velocity. See, that works, right? And then we want to find the motion of this bead. See? Look at that. Okay, so that's what we're going to do right here. There's my thing. Let me turn this camera off because you don't need to see that. So, this is a pretty awesome problem because it's complicated, right? It's complicated because if you wanted to model the motion of this using forces, if I want to say what's the forces on this thing and how would I calculate it, it's pretty hard, right? Because I have the force from the wire, but as this thing rotates, the wire is going to push perpendicular to that. But it's also going to push in and out as the thing rotates. So this force is actually fairly complicated, and it depends on the angular velocity. It depends on the position. It depends on the position of the bead. So it's pretty impossible to do. Not impossible, but it's impractical to use Newtonian mechanics where I calculate the force to find the change in velocity of that bead. Instead, we want to use Lagrangian mechanics. And in Lagrangian mechanics, what we do is to pick some generalized coordinate that can describe the motion of this bead and then minimize what's it called, the least action. Okay, and so we have to find the Lagrangian and then minimize the path integral over space-time. I know that doesn't make sense. I have a video down below. I'll link it down below with my introduction to Lagrangian mechanics. So the first thing we need to think about is how many degrees of freedom does this system have? Because that's how many coordinates we need to represent the motion. Okay, so clearly we could represent the position of the bead along the wire in some way. That's 1 degree of freedom. But what about this rotational degree of freedom? That's not a degree of freedom, right? Because that's something we can change. If this rotates at a constant angular velocity, then that is set in time. So it's not a degree of freedom. And that means that there's only 1 degree of freedom, which is the position of this bead along this. So we can pick any coordinate that we want to describe this. I could have the arc length, but clearly it makes more sense to pick an angle to represent this. So let's move my model out of the way. Here's my bead. Let's call this the x-axis. Let's call this the y-axis. And then z will be out of the page. And then I'm going to call this the angle theta. So theta will be my degree of freedom. So I'm going to need to calculate the Lagrangian, kinetic energy minus potential. And then this is the solution of the equation of motion from the Euler-Lagrange equation, which just says that if we minimize the path integral, then we can get that based on this, where q and qi dot are the generalized coordinate and its derivative. Remember, if I say q dot, that is actually the derivative of q with respect to t. And we use that dot notation because it looks cool and it makes us feel cool. I think this pen's not that great. Let's see if I have this pen that works better. So we have to get the kinetic energy and the potential energy. So what's the kinetic energy of this mass? Let's say it has a mass m, the radius of the hoop is r, and it's spinning with the angular velocity omega. Well, you don't know, right? We don't know what the kinetic energy is. We can't write that in this generalized coordinates. But we can write this. T equals 1/2 m x dot squared plus y dot squared plus z dot squared. In Cartesian coordinates, I know that's kinetic energy. Also, I can write the potential energy, U equals mgy in Cartesian coordinates. So what I need to do is to translate these Cartesian coordinates into my generalized coordinate theta. So I need some type of connection between those. Okay, so at this case right here, I can find the y value of this mass is pretty easy. I can say y equals r cosine theta. All right, that's pretty easy because no matter where this is rotating around, remember this is still, let me draw a top picture. Here's the top picture. So this is going to be equal to, let's see, x cross, so z is coming out. So this is the z, and this is x. And then here's my loop, like that, right? So it's rotating around with this omega. So at any point, this angle right here is going to be, the angle is going to be omega t. It's going to change with time. So if I want to find the x coordinate, if this is x and that's z, I need to know this value right here, which is this distance. So this value is going to be r sine theta. But then I need to project that onto the x-axis right here. So let's say that is equal to sine omega t. So I have two projections, right? One is this projection from the top down. It's this x component, and then I have to project it into the other plane too. Does that make sense? I don't know. It's kind of hard to see. I'll build this in a 3D model, make more sense. Now what about the z component? The z, that's not a dot. Z is going to be the same thing. It's going to be r sine theta. But now I need to project this. Actually, I did that as cosine. Well, it doesn't matter. Cosine omega t, right? So they both have this sine omega t, and then cosine and sine omega t, sine theta, cosine omega t. Okay, so those are my coordinates, and you can see right here that's going to give me my potential energy because I know y. But I need to find x dot squared, y dot squared, and z dot squared to find the kinetic energy. So let's start taking some derivatives. And this can get messy, but we'll just plow through. So let me write it. Y equals r cosine theta. Y dot, I need to take the derivative of this with respect to time. Well, r is a constant, so I just take the derivative of cosine theta. Cosine theta, the derivative of that is sine. So I have negative r is negative sine theta. But then I have to take the derivative of the inside of this, which is theta dot. That's pretty easy. And then I can say y dot squared is going to be r squared, theta dot squared, sine squared theta. And let's put a box around that because that's important. I always feel like Rocket from Guardians of the Galaxy. I put it in a box, right? He had that bomb. I don't know. I shouldn't even bring that up if you don't know what that's from. Okay, now let's look at the x coordinate. So x equals r sine theta sine omega t. And x dot is going to be equal to, now I have a product rule here, so I'm going to take the derivative of this thing first. So I get r theta dot cosine theta sine omega t. So I did skip a step there. I took the derivative of sine is cosine, then I have to take the derivative of the inside is theta dot, and I put it in front. Now I need to take the derivative of this part, so I'm going to say plus r sine theta. The derivative of sine omega t is cosine omega t times the derivative of the inside, which is omega. Omega cosine omega t. Okay, now I need to square that, and this is where it starts getting messy, but don't worry, it's all going to work out. So I have this squared is going to be r squared, theta dot squared, cosine squared theta, sine squared omega t, and then I'm going to get the cross term. Is this minus? Yeah, they're both plus. I'm going to get plus 2r squared theta dot omega, and then I'm going to get a cosine theta sine omega t cosine omega t. And then this last term, I'll put it right here, plus r squared omega squared, I'll pull the omega out front, sine squared theta cosine squared omega t. And I should put that in a box, a red box. Okay, now I have to do z. So z is going to be equal to r, where'd I put it? R sine theta cosine omega t. Z dot is going to be equal to, I I have to take the derivative of this thing first, so I'm going to get r theta dot cosine theta multiplied by that cosine omega t. And then I have to take the derivative of the other part, so I'm going to get minus r omega sine theta sine omega t. Right? Because I took the derivative of cosine omega t, I get negative sine omega t, and then I have an omega derivative of omega t as omega. That's what I get right there. Now let's square this. Z dot squared. It's going to look a lot like that. R squared theta dot squared cosine squared theta cosine squared omega t. Now I'm going to get a minus 2 r squared theta dot omega cosine theta sine omega t cosine omega t. And then I get the last term, it's plus r squared omega squared sine squared theta sine squared omega t. Do you think I should put a box around that? I think I should put a box around that. Okay, so that looks messy. But if I add these together, okay, first let's add these two together. You'll notice right here that this term and this term cancel, right? Because one's minus and one's plus. So that's really good. Now I get this term plus this term. And I can factor out a cosine squared theta. Okay, so let's do that. Let's just focus on the x squared plus y squared. X dot squared plus z dot squared. Okay, so I'm going to factor out this. And I'm going to get r squared theta dot squared cosine squared theta. And then I get sine squared omega t plus cosine squared omega t. And that's going to go away. And then these other terms, I can factor out the sine squared theta. So I get plus r squared omega squared sine squared theta. And then I have, let's see, sine omega squared. Sine squared omega t plus cosine squared omega t. I get that same twice? Let's see. Factor out that. Factor out that. Yeah. Okay. So this is 1. And this is 1. Right? Because I have sine squared plus cosine squared is 1. And so now I just get this. I'm going to add in the y. So I have x dot squared plus y dot squared plus z dot squared. It's going to be equal to this term. R squared theta dot squared cosine squared theta plus r squared omega squared sine squared theta. And then I have the y dot. It's going to be plus r squared theta dot squared sine squared theta. And so right here, I have an r dot squared cosine theta squared theta, r dot squared sine squared theta. So I can combine these two and factor out the r dot theta dot squared, and then I get cosine squared plus sine squared is equal to 1. Let me write that out. So I have r squared theta dot squared times cosine squared theta plus sine squared theta plus r squared omega squared sine squared theta. And that's 1. So I get, I feel like this should be omega t. I get r squared theta dot squared plus r squared omega squared sine squared theta. Okay, I think that's right. Okay, that's my x, and then we can just double check, right? And I should put, that needs a box. Let's put a box like this. Okay. Let's just check the units really quick, because this has units of meters squared per second squared. We know that because these are Cartesian coordinates. This should too, right? So I have distance of meters squared. Theta dot is radians per second. Square that, I get radians per second squared. So I get this whole thing is meters per second. Meters squared per second squared. This is meters squared. That's, again, meters per second, or radians per second quantity squared, and then it has no units. So this does work. Okay, so I have that. Okay, so now we can write down our Lagrangian. So I'm going to write the whole thing. Okay, so L equals T minus U. So that's going to be equal to 1/2 m times x dot squared plus y dot squared plus z dot squared, which is r squared theta dot squared plus r squared omega squared sine squared theta minus the potential. Okay, so but now my potential, let me go back over here. This actually is, my y is actually negative, right? 'Cause if this is my origin, then I'm down here. I left off a minus sign. So this is actually going to be mgy, but y is negative r cosine theta. Now, in my kinetic energy term, that doesn't matter because everything gets squared, so it would work out fine. Okay, so now I get plus mgy, or minus mgy. So it's going to be minus mg, and then I have y is going to be negative, so it's going to be plus r cosine theta. And there's my Lagrangian. And you'll notice it only depends on, the only variables in here are theta dot and theta, and that's what we want. Okay. So now we can use our Euler-Lagrange equation. The partial of L with respect to theta is equal to the derivative with respect to time of the partial of L with respect to theta dot. So let's start right here and take the partial of L with respect to theta. And that's going to be equal to, okay, what terms of theta in there? Here's one. So I have a 1/2 m r squared omega squared sine squared theta. So I have to take the derivative of that. So I'm going to bring the 2 down, and I get m r squared omega squared sine theta. Now I have to take the derivative of sine theta, which is cosine theta. Now I have to take the derivative of the inside of that, which is theta dot. Okay, so that's the partial of this with respect to theta. Now I need to take the partial of this with respect to theta, so I get minus mgr. Oh wait, there's not theta dot. It's a partial with respect to theta, not theta dot. Not an actual derivative. So it just ends right there. Minus mg sine theta. Okay, so that's my partial of L with respect to theta. Now I'm going to take the partial of L with respect to theta dot. Okay, so what terms have a theta dot? Here's one. So I'm going to get a power of 2, bring down 2 over 2. It's going to be m r squared theta dot. I haven't taken the time derivative yet. Are there any other theta dots? They are not. Okay, so now I can take the derivative with respect to time of the partial of L with respect to theta dot. And that's just going to be the derivative of this with respect to time. That's a constant, that's not. So I get m r squared theta double dot. Now I can set this equal to that, and I get m r squared theta double dot equals m r squared omega squared sine theta cosine theta minus mgr sine theta. And that is my equation of motion. And I think that's right. It could be wrong, okay? I did all this and easily could have made a mistake. And if I did that, I'm going to stick by the methodology, even if I made an error. Okay, but we make errors sometimes. Okay, so now how do I solve the equation of motion? I mean, this is a complicated differential equation, so we're not going to solve it the normal way. We're going to do a numerical solution. So let's go back over to a new page, and let me write that equation down again. Now, I gave this as a test question, and in the test question, that was the answer. I said find the differential equation of motion. You didn't have to find the whole thing. Okay. So let's say m r squared theta double dot equals m r squared omega squared sine theta cosine theta minus theta minus mgr sine theta. Okay, so the first thing I want to do is solve this for theta double dot. So I'm going to divide both sides by mr squared, and I get theta double dot equals, notice that the m's in all the terms, it cancels, and this r squared is going to cancel, so I get omega squared sine theta cosine theta, and then over here I get minus g sine theta over r, because it was, I had an r, I divided by r squared, so I just get that. Okay, just double check here. This is radians per second squared, and this is meters per second squared divided by meters is 1 over second squared, so the units all work. Okay. Now, how do we model this? Here's where we're going to do numerical calculation. Suppose that I take a small time interval, delta t equals 0.01 for right now, and I need some values. So I need r equals, how big is my thing? What if I use this actual, what if I use this? Okay, so this was, what's that, 5 centimeter radius? Let's just say 5 centimeters. So 0.05. The mass doesn't matter, but let's say that's 0.1. And then I need omega for the rotating disk. Let's say it's 4. No, faster than that. Let's say 10 radians per second. And now I need my initial theta. Theta 0 equals, I don't know, 45 degrees. I'll convert that to radians. I need my initial theta 0 dot. Theta dot 0 is 0. Okay, so those are my initial conditions. If I have that and I break this into a super small time interval, then I can calculate my angular acceleration theta double dot using these variables. Okay, and so I'm going to assume that theta is constant during this 0.01 seconds, and I don't have theta dot in there. That's strange. Okay, let's just keep. Oh, I did have a theta dot. No, I didn't. Okay. So let's assume theta is constant during this time interval, and then I can say the following. I can calculate this. This is step 1. Theta double dot equals. I'm just going to calculate that right there. Now, at the end of that time interval, I can calculate theta dot. So I know this. Theta double dot is equal to the change in theta dot over the change in time. And I'm going to assume that's constant over this time interval. So this is going to be equal to theta dot 2 minus theta dot 1 over delta t. If I solve that for theta 2 dot, I get this. Theta 2 dot equals theta 1 dot plus theta double dot delta t. This is not right, okay? But if delta t is small enough, then this can work, right? Because I'm assuming that theta double dot is constant over this time interval, which it's not. Now I can do the same thing for theta. Theta dot is the change in theta over the change in time. So I can solve for, this is going to be equal to theta 2 minus theta 1 over delta t. Now I can solve this for theta 2, and I get theta 2 equals theta 1 plus theta dot delta t. Now I just calculated theta dot 2 at the end of the time interval, so I'm going to use that theta dot. Even though it's not constant, even though this is not right? This assumes that theta dot is constant, and I'm just going to use the end velocity. Okay. Now lastly, I'm going to say this, t2 equals t1 plus delta t. And then I'm going to go back up here and do this again. So this will give me the theta dot and theta at the end of the time interval. And if I want to get it at 0.02 seconds, I have to do it again. And now I'd have to recalculate theta double dot because theta changed. And that would mean I'd recalculate theta dot and theta. And so I'd keep doing this over and over and over again. And this is the Euler method of numerical calculations. And there's different versions of these. There's more accurate versions of these, but this should work. As long as I pick a small enough time interval, then this will work. So let's do that. Okay, I'm going to do that and just calculate theta as a function of time and plot it using these initial conditions. But I have to have initial conditions. I have to have actual values because I'm actually calculating numbers here. That's why it's called a numerical calculation. Okay, so let's jump over to, I'm going to do this in Python. You don't have to do this in Python. You could do it on paper. You could do it in a spreadsheet. You could do it in C++. You could use Java. You could use Fortran. I like Python. Okay, so I have a nice version of Python online that I can use. Let's switch over to that. Okay, so this is trinket.io. It's just Python in a web page. So I'm going to type in my initial conditions first. So I had r equals 0.05. Omega, I'm just going to use W. Omega, what did I say what that was? 10. And I don't want to put units here, okay? Because if I put units, then Python doesn't understand that that's a number. Python's not that smart. You got to be smart. M equals 0.01. I didn't even use that. I didn't. Theta is going to be 45. I need this in Python's going to use radians, so I'm going to convert this to radians. 45 times pi divided by 180. Now it's in radians. There is another way to convert it, but don't worry about that. Theta dot, I'm going to call this, let's call it theta dot equals 0. Okay. When you're writing variable names in Python, case does matter, and you have to spell it the same way each time, but you can call it whatever you want. What else do I have? Omega r, d, I need t equals 0. dt equals 0.01. And now I'm actually going to make a graph on a plot. Theta is a function of time. So I'm going to make a graph. T-graph, I always call it T-graph. Is one of the nice things about, I'm using GlowScript v Python. It has built-in graphing that makes things really easy to graph. So let's just give it a title. Hoop, spinning hoop. I don't know. With bead. And I'll give it an x title time in seconds. And then I'll give it a y title, and that's going to be equal to theta. Let's do, should we do theta in radians or degrees? I always feel like I think in degrees. Let's do degrees. And that's just a word, right? And let's do this. Width equals 500. Height equals 350. So I find that when I run it, they'll resize the graph so it's easier to see and I don't have to scroll all over the place. Okay, so now I can do my calculations. And how many of these do I want to do? Let's do it for 5 seconds. So I'm going to say while t is less than 5, colon. Now this is a loop in Python. Everything below this that's indented will be part of the loop. Once I dedent, it's no longer in the loop. So the first thing I want to do is calculate theta double dot. So I'm going to say theta d dot, that's my double dot. And now I'm just going to type in the equation I had over here, which is omega squared, which is w squared. In Python, squared is star star, and I always get scared that it's going to do something else there, so I put that in parentheses. Sine theta times sine theta times cosine theta minus g times sine theta divided by r. And I don't have a g, so I got to put that up here. G equals 9.8. Now in this case, I'm using g as a scalar gravitational field. So don't put negative there. I've already included the negative when I calculate the potential. Okay, so that's theta double dot. Now I can use that to calculate theta dot. So theta dot equals theta dot plus theta double dot times dt. So this is in Python, this looks crazy, but it's not. This is not an algebraic equal sign. This is a make equal to sign. So I don't have to put theta 1, theta 2, theta 3. I just say theta, and it updates theta, theta dot. But it does do theta 2, so let's do theta. Theta equals theta plus theta dot times dt, and then update time. T equals t plus dt. Okay, now I need to graph. Oh, I made my graph, I didn't add a function to graph. So say f1 equals g curve, color equals color dot blue. And down here, I'm going to say f1 dot plot t theta times 180 divided by pi. So when I plot the theta, I'm converting it back to degrees because I wanted it in degrees. I just like it that way. Okay, let's save this. Rotate hoop 1. And now run it. So, is that right? Theta oscillates up and down. I don't even know if that's right. Okay, how about this? I do know one case where it should be stable, right? I can calculate a stable position. So if I put it there, it should stay there. So let's go back over to the paper and see if that, I feel like this does not look right. Or how about this? What if I put omega to 0? Then this should just be like a pendulum. Yeah, it does. I'm looking at my thing. So if I put omega is, let's put it at 1, very low. That's the same thing. It looks the same. Put omega 0. Theta double dot. I'm looking at my thing. Theta double dot. Theta minus g sine theta. Theta dot plus theta double dot. D dot times gt. Theta equals theta plus theta dot times gt. Let's put theta at 90 degrees. Oh, no. I have it as, let's put it at 0. So now I'm starting it straight at the bottom. And if it's not rotating, then it should stay there. Okay, that worked. That worked. Now if I increase that just a little bit by, let's say, 10 degrees, it's not rotating. It's going back and forth between 10. I think that's okay. Let's put this at 10 degrees with an angular velocity of 10. Okay, so that is different. That does look different. Let's put this at 100. Let's put it at 50. Okay, so it's oscillating. Okay, look at this. See, so it actually went up and it's oscillating about a different point here. Oh, it is oscillating back and forth. I think this is okay. I think this is okay. So let's put this back at 5. I don't know what I'm doing. Okay, what was I going to do? Oh, the stable orbit. Okay, so let's go back to the paper. So let's suppose I have my ring like this. Here's a side view. And here I have a bead, and this is the angle theta. Now let's think about this in terms of a stable position. I can calculate the forces. I have the gravitational force mg, and then I have the normal force right there due to that. But it's not moving up or down, so it's stationary. And this is rotating with some velocity omega. So this is the radial, this is moving in a circle, right? And if it's moving in a circle, then I can say Fr equals m omega squared r, that's r, right? Because that has to be equal to, the radial forces has to be equal to the mass times the centripetal acceleration. Now, the radial force, gravity is pulling straight down, but the normal force does have a component in that direction, and it would be, let's see, in sine theta. So I can say in sine theta equals m omega squared, and r right here is going to be, this whole thing is r, is going to be big R sine theta. Is that true? So that's going to be, yeah, I guess so. Okay, so these cancel, and I get n equals m omega squared r. But I also know that the acceleration in the vertical direction is 0. So n cosine theta equals mg. Those have to add up. So n is going to be mg over cosine theta. And this is only in the case of a stable orbit, right? So if I put that up here, I get mg over cosine theta equals m omega squared r. And if I solve this for theta, cosine theta, I get cosine theta the mass cancels. Cosine theta is going to be g over omega squared r. And let's see, that's meters per second squared. Okay, that works. Yeah. So theta is going to be the inverse cosine of g over omega squared r. If I put it at that initial location with an initial velocity of 0, it should stay there. So let's check. And if it doesn't, I'm going to quit, and I'm going to be sad, but I still think this was a worthwhile video. Okay, so I'm switching back over here to the computer. So let's calculate that. Let's calculate, I'm just going to recalculate theta. Theta equals arc cosine of g divided by omega squared, so r times omega squared. Okay, so that should just have a straight line here. I'm kind of scared. No, something happened. It didn't do anything. Theta equals, why didn't it print anything? Theta equals a cos g. Let's print that. Oh, it's not a number. G r squared, r times omega squared. So I don't have, I guess my omega is too high. Let's see if I put this lower at 1. Not a number. G is 9.8 divided by, let's just print this. $196. R, why is it 196? Omega squared is 1. R is 0.05. Gee, okay, that's true. So I need a larger omega. So let's put this at 15. Okay, that's at least getting somewhere. This is, ooh, that's weird. Let's put it a little bit higher. Why is it doing that? That's really weird. Okay, so this is 40. I think it's just going back and forth. It's actually, if I can fix this with the smaller time interval, I think. Okay, it's just oscillating back and forth between numbers that are almost around 47 degrees. I think it's working. I think it's working. Okay, now I do want to do one other thing. I wanted to make a visual model of this, but I don't want to do it today. Okay, so let's save that. Let's just see right here if I go to Trinket and make a new, actually I could just do this. Let's copy this. And then the key here is I'm going to make a visual of that. So I can make a ring in 3D and rotate it around with the bead on there, and you can see what it looks like. And I do want to do that, but I'm afraid that I might get bogged down in the details. I could just go for it though, you know? It's a 38-minute video right now. What do you think? What do you guys think? Are you worn out from this? I want to just do it. I don't want to make another video. I'm going to do it. Okay, so let's make a ring. So let's say, let's go down here. Let's start my visual self. So I'm going to make, I only need 2 things. So let's make loop. No. I can't say ring. Hoop. Hoop equals ring. Okay, so over here, the properties of the ring, I have the position. I'm going to put that at the where the center of the ring is. The radius, I have the axis is the vector pointing in the direction of the axis of the ring. And then I have the radius of the ring and the thickness of the ring. Okay, so there's a lot of stuff there. Okay, so let's see if we can make this. Ring, position equals vector 0, 0, 0. Radius equals r. Thickness equals, let's say, r divided by 10. And then axis equals, you can put this in any order, it doesn't really matter. Axis, I want to point it in in the z direction, right? So in Python, up is y, to the right is x. So it's going to be axis of vector 0, 0, 1. Let's see what happens. I made a ring. Check that out. Okay, it's a little too thick. So I want to make that thickness, say, divided by 20. And I'm going to leave it as, make it a little bit thinner, 30. Okay, now let's make the bead. Bead equals a sphere. Position equals r times vector. It depends on this angle theta. You know, this is going to be kind of hard because I need to model the motion. Yeah, I'm just going to show you how to get this started, and then I'll make another video because I'm going to make this. It might be a little bit harder to make. Actually, I think I might just write it up as a blog post. Okay, so theta. So I have r times vector cosine theta, which I already calculated theta, then negative sine theta, and then 0 in the z direction at this instant. And then the radius is going to have to be bigger than the thickness. So let's say r divided by 20, and let's make it yellow. And let's run it. There, okay. So I'm going to make that bead slide up and down in real time as the disk rotates. And here's the problem, right? Because as I rotate that disk, that ring, then I need to calculate the Cartesian coordinates of that hoop. And I think it's not so bad since I already I calculated x, y, and z in my Lagrangian. So I think I actually could do this. But I do need to rotate that. I need to change the axis of that. Yeah, and I think I'll just do it. I'll write this up. Yeah, I'll just write it up. I'll write up this blog post. Okay, and then, but I'll include this link down below, and you guys can play with this. Maybe you can build this and have fun with it. And that's it. That was a fun problem. Okay, that's it. More physics later.